The North Sea, separating Britain from Northern Europe. Its waters stretch over 289,000 square miles. It's a famously hostile environment. Storms bring 20-foot waves, whipped up by nearly 70-mile-per-hour winds. Challenging conditions for one of the world's busiest shipping areas, whose traffic must also navigate shifting sandbanks. It seems an impossible place to build. But these awe-inspiring natural forces are irresistible to a group of intrepid engineers. Around 12 miles off the British coast, an ambitious project is taking on these waters.
It's a hostile environment, and it presents a major challenge for any kind of engineering construction.
But this is an unprecedented engineering marvel. The London Array.
London Array is the world's largest offshore wind farm.
175 towering turbines capture the energy of the wind and convert it into record-breaking levels of electricity.
On an average year, the wind farm produces over 2 billion units of electricity. That's enough to power 500,000 houses.
It's an army of giant spinning windmills that covers more than 38 square miles.
Right now, we're about 87 meters above sea level. You can see the rotor behind us, so each blade length is 58 meters. Standing out on these machines, it really does make you feel what a unique place to be.
London Array's turbines reach almost 495 feet above sea level. Each blade is almost as long as a jumbo jet's wingspan. Embedded in 716-ton foundations, they feed into 125 miles of cabling. 2 offshore substations send all this power to the mainland, where it provides enough electricity for 500,000 homes. But engineering on this scale at sea has never been done before. And this unpredictable environment presents huge construction challenges.
There was a really ambitious plan to build a wind farm here. It's quite tidal restricted. There's a lot of change in tidal height, so there's very high currents, a lot of moving sandbanks.
The brutal marine environment also takes its toll on any technology. And Captain Nick Coville is part of the team making this immense wind farm a reality.
If a piece of equipment fails, we're working to a very, very small weather window. We can't nip to the local hardware store and get another one.
But above all, in the middle of one of Europe's most extreme locations, these turbines must somehow generate year-round power on an unparalleled scale.
We need to generate electricity 24 hours a day, 7 days a week, in this remote offshore location. It's an unforgiving and unpredictable environment.
Out here, the challenges are enormous. The team must do whatever they can to keep the blades turning. So how is it even possible to harness the power of the wind? Dr. Andrew Steele is on the windswept coastline of Scotland, searching for the relics of an idea that sparked an engineering revolution.
This 18th century salt mill is one of Scotland's best preserved windmills. The principle behind a windmill is simple. By taking linear motion from the wind, spinning those giant sails and creating a rotary motion, you can then use axles and gears to take that motion to wherever you want to use the energy.
This windmill would have once had large sails. Its rotation was used to pump seawater onto the land for the production of salt. It was a technology that hadn't changed for thousands of years. Just like today's engineers at the London Array offshore wind farm, Scottish engineer James Blythe was determined to generate electricity from wind power. And in 1887, in his garden on the coast, he built the world's first wind turbine to power the lights in his cottage. But it said his neighbors weren't impressed. They considered electricity the work of the devil. Andrew Steele, however, has managed to track down a place that welcomed Blythe's innovation.
Although Blythe's design didn't prove popular with the locals, he did manage to find a new home for it here at Sunnyside Hospital, or as it was known then, Montrose Lunatic Asylum.
With electricity supplies in this era notoriously unreliable, Blythe proposed adding his new wind turbine invention. Blythe attached his generator to an accumulator, an early form of rechargeable battery, and his invention was an instant hit.
Blythe's design was so successful that it actually stood here and powered Montrose Lunatic Asylum for 30 years before it was demolished.
London Array's 175 turbines are over 10 times taller than the Montrose turbine, reaching 482 feet from base to blade tip. While Blythe used horizontally rotating cylinders, the Array uses 190-foot-long vertical blades to squeeze as much electricity as possible out of the North Sea's powerful winds. The vital job of ensuring the turbines remain operational falls to a team of specialized engineers. When they're called into action, they must first make the over 12-mile journey out to sea.
We have 175 offshore power generation plants, so we need to send people offshore to keep all of the turbines running all of the time. It's quite an extreme job. The guys have to be tough and they have to be capable of meeting physical demands.
They have extraordinary access to the hidden inner workings of these incredible structures. Today, Senior Operations Technician Ronnie Hill must carry out essential maintenance to the turbine known as Echo 19.
Hi Rob, it's Echo 19. Shall I take control please under AWP?
Yep, that's on copy 013, and there's no restrictions.
Before work can begin, he must access a control panel on the lower platform to bring the blades to a standstill.
So you can already hear it's starting to slow down. There we go.
Each giant tower contains an elevator to assist team members like Senior Engineer Ed Hall with at least some of the 230-foot ascent.
So that's the lift part of the journey over. It's quite a challenge just getting access to the point of work. Yeah, now we've got to climb up.
The heart of the turbine is known as the nacelle. A 33-foot-long stainless steel enclosure, the nacelle houses the machinery needed to produce electricity from the blades.
Not many people get to see this part. It's very unique. This is the nacelle of a turbine where all the action happens. So this is where the power is getting generated and transmitted. We have the rotor at the front with the blades. So that rotational energy is transferred through a gearbox. And behind me, we have the generator where the electrical energy is produced.
The energy from the turbine's blades can produce electricity in as little as 7-mile-per-hour winds. The turbine blades rotate an input shaft at up to 13 revolutions per minute. A gearbox makes the output shaft spin more than 100 times faster. A generator then converts this increased kinetic energy to electricity.
So the task we're given today is lubricating the main bearing. Those look like bearings in your car. Over time they wear out. The more we lubricate it, the longer it keeps going, the more power we can produce. This is what we're here to do at the end of the day. There we go. These machines, they don't stop. Summer, winter, Christmas Day. They still got to run, we still need electricity.
Constructing just one of these megastructures is a huge engineering challenge. So how do you make 175 of them when your building site is the North Sea?
And not only do you have challenging seabed conditions, you also have different depths. It's a challenge from start to finish.
These 175 turbines make up the world's largest offshore wind farm, the London Array. For head of operations Graham Dawes, it's a perfect location for a bumper harvest.
Around the coast of the UK, we have more wind energy than pretty much the whole of the rest of Europe.
Spanning an area over 38 square miles, these nearly 495-foot-high turbines are kept operational 24 hours a day, 7 days a week, to produce 2.5 billion units of electricity a year. Each of these massive marvels is made up of mammoth components.
The tower itself in two parts weigh around about 200 tons. Each one of those blades is around about 25 or 30 tons each. And then the cell, the part that goes onto the top of the wind turbine, they can be up to 300 tons.
But constructing this army of giants in the unforgiving North Sea is the biggest battle of all.
The weather conditions can be very variable. We can have mist and fog as we have today. You can have nice flat calm seas, and you can also have storm force conditions rolling in without warning.
It's a significant operation to install one of these turbines. Fast flowing tides, the nature of the seabed is extremely variable. So even in one location, we could get a difference of up to 10 meters. The change is very, very extreme in a very, very small area. It's a challenge from start to finish.
So how is it possible to create a stable structure when your building site is underwater? Aromanche in northern France is the site of an historic marine construction breakthrough. Today, Dr. Rhys Morgan is joining a team of divers who are tracking down an engineering relic.
This coastline is the site of some of the most incredible Second World War engineering, and we're on the hunt for perhaps its most ingenious component.
Lurking in the depths since the 1940s lies a game-changing innovation that has influenced countless future engineers like the team at London Array. During 1944, the D-Day landings gave the Allies a toehold in Europe, but this was just the beginning. To free the Nazi-occupied continent, they faced the problem of landing enormous quantities of equipment on the Normandy coast.
To take on the mighty German army, hundreds of thousands of troops and their vehicles had to be landed on the beaches behind me.
British engineer Sir Bruce Gordon White had to carry out an astonishing plan. Construct 2 fully functioning harbors in a matter of 2 days. And it would have been impossible without a brilliantly simple piece of engineering called a spud leg.
There it is.
Ah, look.
There's the edge of it. It's definitely got an upright. 7. One spud leg.
Fantastic! We've actually found one of the original spud legs on the seabed. It's incredible to think that these now discarded pieces of metal were once vital for ending a terrible war.
The spud legs were the vital component that made Sir Bruce Gordon White's famous Mulberry Harbors possible.
These big concrete blocks behind me were floating pontoons on which a steel roadway led out from the beach to the deeper water, so that the ships could unload their tanks and they could drive right onto the beach. Creating a floating pier is one thing, but anchoring it securely in tidal waters and making sure it's stable enough to carry a tank is a whole other ballgame.
The engineers building the London Array need a solid, stable platform to work from. Gordon White needed something similar in order to safely land trucks and tanks.
This simple platform illustrates the problem. In normal conditions, it's fine, but if you've got rough seas, then actually it's very unstable. it will swing violently from side to side, potentially damaging the roadway. So it needs to be anchored. Now, the problem is, if you have a fixed anchor, as the tide comes up, the platform itself starts to sink.
Surviving the seas required a special solution, and the answer was movable mechanical legs, which allow the pontoon to go up and down.
These 4 legs help the platform remain stable. They weren't driven into the ground, but rather the ends just sat on the surface of the seabed. Now, the weight of the platform, connected by these chains, is forcing the legs down, and that acts as an anchor. Not only did the legs prevent the platform moving from side to side, but the tension in the cable could also be adjusted to rise and lower with the height of the tide. Just a brilliant idea.
Thanks to inventive engineering, over 2 million men were landed alongside 500,000 vehicles and almost 4.5 million tons of goods. The remains of this remarkable invention may be hidden in these French waters, but it has inspired engineers around the world. The spuds were an ingenious solution for Normandy's shores. But how could movable legs be used to construct a wind farm in the middle of the North Sea? The answer lies in an extraordinary vessel.
This is MPI Discovery. 20,000 tons of hydraulic muscle. At the time of London Array, she was the fastest, had the highest lift, had the fastest turnover rate in the world. These ships were pretty much designed with the London Array project in mind.
Discovery can construct the seemingly impossible thanks to a mind-blowing metamorphosis. From ship to offshore building platform in a matter of hours. Experiencing this jack-up ship in action is a unique experience for Captain Nick Coville.
When you're slightly pitching and rolling as you do at sea, to the legs taking the seabed, everything stops and you become a platform.
Like a supersized version of Bruce Gordon White's solution for the Normandy invasion, MPI Discovery uses giant legs to act like a table sitting on the seabed.
Discovery itself has 6 legs. From the bottom of the keel to the top of the leg is about 75 meters. You can see here they're probably about 4 or 5 inches of steel.
The British Army's spud legs were winched, but Discovery's rely on hydraulics. Each leg is jacked up by 8 huge cylinders, with every vertical movement secured by a massive pinning system.
Each one of these cylinders is capable of lifting 500 tons. You have 2 cylinders here that go to a single yoke, and you have a pin that withdraws. The yoke comes down, the pin goes in, and then the leg is either raised or lowered, depending on whether we're recovering the legs or driving them into the seabed. The system here is capable of lifting 24,000 tons of ship, all the components for 8 turbines, completely clear of the water.
This ship can remain stable in depths of up to 130 feet. But in order to assemble the component parts for the wind turbines, it needs even more muscle. Thanks to the inspired engineering behind Bruce Gordon White's spud legs, MPI Discovery can provide a stable base for the complicated process of constructing a record-breaking wind farm at sea. But Discovery can't do the building itself. The team needs another mechanical giant to assemble the enormous turbines that turn the North Sea's winds into massive amounts of electricity.
So here we have a 1,000-ton crane, a unique piece of equipment. There was no other crane available that was so compact, that had such a lifting capacity.
This mega machine can assemble the superstructure of an entire turbine. First, a hydraulic hammer is used to drive a giant 18-foot diameter steel tube, which can weigh up to 715 tons, to depths of up to 223 feet below the seabed. This holds in place a yellow transition piece, which can be up to 92 feet high. Next, the main tower is added, topped off by the nacelle and hub. 3 190-foot-long blades complete each 530-ton structure. Amazingly, 8 turbines can be transported and built on a single voyage.
So the reason that we have such a vast deck space is basically because of the size of the wind turbine components. The nacelles are the size of 2 or 3 double-decker buses. We have 8 of them in the centre of the ship. The blades run across the vessel, going actually over the side by about 30 metres. My first day as captain, the London Array team told me that I must not roll the ship more than a certain amount, otherwise the blades will go in the water and get damaged. And I was thinking to myself, what have I let myself in for here, really?
But the wind turbines themselves are just the start of this impossible engineering feat. Each turbine forms part of a 124-mile network, converging at one of the 2 gigantic offshore substations. These perform a vital role, boosting the voltage produced by the turbines before sending it to the mainland.
So there behind me you can see one of the 2 London Array substations. These structures are critical to the operation of the London Array. All of the energy that's produced passes through one of these 2 substations. They perform a critical function in increasing the voltage from 33,000 volts to 150,000 volts in order to minimise the losses as the energy transitions on its long journey back ashore.
4 huge cables over 30 miles long are needed to complete this final leg. Each weighing nearly 5,000 tons, they are floated towards the Kent coastline and then sunk to the seabed as they finally converge at Cleve Hill onshore substation.
This is where the 630 megawatts of energy produced by the London Array offshore wind farm out there comes ashore on the North Kent coast. The 4 large cables comes through this field and then joins the UK national grid.
Harnessing the elements to create colossal amounts of electricity is an engineering triumph. But there is such a thing as too much wind. The turbines must be able to stand up to a battering from the brutal storms that afflict this dangerous sea.
Our turbines are 12 miles out at sea. We encounter all sorts of weather, from rough seas to high winds to extreme hailstones and rain. The turbines can operate quite safely into wind speeds of up to 50 miles an hour. Beyond 50 miles an hour, the turbine needs to be able to protect itself. One of the challenges that the team who designed the turbines had to overcome was finding ways of being able to allow the turbine to protect itself in extreme weather conditions.
So when the extreme weather hits and wind speeds reach 50 miles per hour, exposed to the North Sea's punishing conditions, how can these vital mega machines survive the very elements they're trying to harness? Deep in the Danish countryside is an extraordinary structure that Dr. Tuffe Gochman is scaling. And it might hold the key to weatherproofing the London Array.
I'm 54 meters off the ground right now. And this 2 megawatt design machine has been operating at this very spot for the past 40 years. That is by far the longest operational time for any wind turbines in the world. And it has a beautiful view.
In 1978, the giant Tvindkraft dwarfed all wind turbines before it. To date, its 88-foot-long blades have completed over 120 million revolutions.
It has produced more than 21 million kilowatt hours. To put that into perspective, that kind of production could power up the entire New York City for more than 3 years.
The London Array produces enough clean energy to power 500,000 houses every year, and the engineers behind this groundbreaking wind farm owe it in part to an unlikely group of visionaries from the past. In the 1970s, the world was gripped by an oil crisis. Denmark was no exception. So a group of radical teachers set up a collective, promoting the country's strong winds as a viable energy alternative. On a farmland plot called Tvind, they mobilized hundreds of volunteers, building the seemingly impossible with little financial backing.
What I really love about the Tvincraft turbine is how many second-hand components you can find here in the nacelle. For example, this main drive shaft over here is from an oil tanker, and this gearbox right here is from a copper mine, and the generator is from a paper factory from Sweden.
But as at the London Array, the sheer scale of Tvincraft posed enormous challenges. No manufacturer could be found to construct the 88-foot blades, so the collective took matters into their own hands, breaking the mold of blade design.
They're not made of metal, which was popular at the time, but they're made of glass fibers, which give them a lot of flexibility.
Designed to withstand a hurricane, the massive blades can flex almost 5 feet in either direction. But this rotor has another ingenious way of dealing with wind.
Arguably, the most important innovation of Tvincraft is actually being able to pitch the blades.
To maximize efficiency, pitching orients Tvincraft's blades at various angles to the wind.
I have this little version of Tvincraft with me here. We have the blades pitched to the ultimate efficiency position already. We will give it some steady wind, and then get a reading out of that. So right now, my little twin is producing about 0.15 volts.
But if the angle of the blades is turned to a less efficient position,
we are actually adjusting them approximately half the way. We can already see that it's rotating a lot slower. And the reading I have is actually around 0.7.
But pitching can have an even more dramatic effect.
I'm changing their angle so that they will face the wind almost entirely, eliminating the lift that is created by the turbine blades. And when I take my hands off, no more rotation.
The Tvincraft collective had engineered a truly adaptable turbine that could safely survive a storm and maximize energy in a steady breeze. From these humble beginnings, it wouldn't be long before the commercial world took notice. In the 1980s, around 700 Danish-built turbines were ordered for a site in California that would eventually become the world-famous Tehachapi Pass wind farm and spell the start of the Californian wind rush. At 190 feet long, the blades of London Array's turbines are twice the size of Tvincraft's. But incredibly, they're able to maneuver in the same way. Engineer Ed Hall has special access to take a closer look.
The blades on these wind turbines can pitch. The advantage of pitching the blades is to allow a variable speed production. A greater amount of energy can be captured at lower wind speeds. And in terms of also providing a safety function for stopping as well, it's important that the pitch system can pitch the blades out quickly if the turbine needs to stop.
These intelligent blades are even able to angle to the optimum position automatically, thanks to a clever onboard computer which operates a system of hydraulics.
One of the special things we can do is change the pitch angle right now for working on different areas of the blade. So as you can see, the pitch angle moves relatively quickly. All the blades can move independently, continually changing the angle to optimize itself for the wind conditions present.
The blades themselves are molded from a single piece of fiberglass, making them lightweight but super strong. The circular base of each one is bolted onto one of 3 connection points on the nose of the turbine. a 10-foot-high fiberglass dome known as the hub.
So right now we're in the hub of the turbine. So this is right at the front of the machine, between the blades, and 90 meters above sea level. Here we can see the 3 blades bolted on here, here, and here. The benefit of having a single piece design is so there's no jointed connections, which have historically in the industry been the weakest point of blades in their design. So to have it molded in a single piece is really key in the technology development. Inside the blade is actually hollow. You can get inside and move along it and walk inside it. It's that large. This is the evolution of a number of years, up to 30 years development of wind turbine blade design.
London Array is so efficient, its annual contribution to the reduction of CO2 emissions is the equivalent to taking around 290,000 cars off the road. But with the pressure on to produce even more power, how can engineers here take it to the max?
Wind is a free fuel, so it's all about getting the most out of it that you possibly can.
In 2013, the vast London Array rose out of the North Sea, delivering more energy in a single month than any offshore farm before it.
Nothing on this scale had been done before, so it was a real step change in terms of the real size and capacity and the challenges faced.
Spread over 38 square miles, the 175 turbines are arranged in a giant grid to capture the North Sea's prevailing southwesterly winds. Each turbine is computer-controlled, with all data sent back to the control room on the mainland.
This is the London Array Operations Control Room. This is the nerve centre for controlling all operations that happen on a daily basis. We're looking at the performance for the previous month. The table of information there in the centre of the screen is giving an indication that we would have hoped to produce about 192,000 megawatt hours. We actually produced 208,000, so we produced more than budget, which is, again, a very nice feeling, and is generally as a result of the wind blowing rather more than expected. The future is going to be much larger wind farms, much further offshore with much larger turbines. So the future is looking very rosy indeed for offshore wind.
But to stay at the cutting edge of this new technology, the challenge for this ambitious team is to maximize the array's potential.
It's all about coming up with new ways to really optimize the efficiency. So when the wind is blowing, we're able to capture all the energy that we possibly can.
But how is it possible to boost the power of the array? To unlock the secret, its engineers, in their quest for kilovolts, must turn to an unlikely source. Britain's Silverstone is home to a high-octane sport where performance is everything.
It's a beautiful day for racing.
But engineer Dr. Aisling O'Kane is finding out that despite the huge horsepower on display at this classic meet,
It's amazing to be close to this speed and this power.
a secret to slashing lap times is surprisingly small, and was invented over 40 years ago. Created by American racing legend and engineer Dan Gurney. In 1971, his All-American team car was struggling with performance, lacking the edge to be an Indy 500 contender, until Gurney bolted on an addition to its wing.
Here it is, the Gurney flap. Small piece of engineering, massive difference to downforce. And Dan Gurney had happened upon in his garage a significant feat that even the aerospace engineers hadn't come across yet.
It might not look impressive, but this tiny detailing has a big effect on turbulent air, known as vortices, formed at the airfoil's trailing edge.
On a normal airfoil, there are two vortices that come out and meet in the middle. But the addition of the gurney flap, that changes these vortices in a very significant way.
The flap's additional height changes the point at which the streams of air separated by the wing reconnect, increasing the vertical deflection of air, creating greater downforce. But how much can that minute metal addition change the aerodynamics of a wind turbine as tall as the Great Pyramid? It's no surprise that for the engineers behind the London Array, the largest offshore wind farm in the world, aerodynamics are an important consideration. To maximize the output of these gigantic wind turbines, they must turn to an invention from the past, the gurney flap. Dr. Aisling O'Kane demonstrates how this tiny innovation packs a big punch.
We're going to use this model airfoil, put it on the scales, and see how downforce is created. So you can see there it's 0 grams. We're going to take our trusty instrument to create the air force. The air coming through is creating low pressure underneath, high pressure above, and therefore creating downforce. The readings here hovering between 10 and 15 grams.
But when a gurney flap is added, the difference is remarkable.
So look, you can see the grams are approximately twice what they were without the gurney flap. It's doubled the downforce. The power of the gurney flap has massive impact, even on this model.
Gurney's newly improved Eagle claimed 7 pole positions and won an impressive 4 IndyCar races.
At places like this, where there's such competition in race car driving, they're pushing vehicles to the limits and pushing the physics involved in it. The impact that it had to engineering is absolutely amazing.
But how can London Array's engineers adapt this minuscule concept to enhance the largest offshore wind farm on the planet? Each of the 175 turbines are supersized, but Ed Hall and his team are making small adjustments to evolve its blade technology.
Increasing aerodynamic efficiency on these blades, we use a number of aerodynamic enhancements. It's about reducing drag and getting as much energy out of the wind as possible.
Inspired by the gurney flap, a serrated strip is fitted along the edge near the center of the blade, helping produce more lift, which makes them spin faster. Serrated tails are also fitted to the fastest moving part of the blade to reduce drag caused by turbulence.
The add-ons add a % or 2 onto the energy that we can capture from the wind. Doesn't sound like a lot, but when you add it up over 175 turbines here, operating 24/7, then it does add up.
In this offshore world of mammoth engineering, it's the smallest details that can make the biggest difference.
Using different elements of engineering to really maximize the amount of energy that's captured from the wind is really exciting. Wind is a free fuel, so it's all about getting the most out of it that you possibly can.
These final modifications to the blades are the finishing touches to one of the world's most advanced maritime feats of engineering.